Determine if the following set of polynomials, p sub 1 through p sub 3, is linearly independent. So to get us started here, we want to recall the standard notation for a polynomial defined by some vector space p sub n. And so we have that standard form here. And the vectors that we're checking are the vectors made up by the coefficients. So looking at what's given to us in this question, we can see that we are working with polynomials of degree 1. So that means each polynomial, p of t, is defined at most by a naught plus a sub 1, t to the first. And so the vectors that we're checking, so in this case we'd have some vector p defined by two components, a naught and a sub 1, the coefficients of the polynomial. So we're going to create our indexed set of vectors using the coefficients of each one of these three polynomials. So here we go. Our first polynomial, p sub 1 of t, is defined as 2, so it's just a constant. So we can say that the vector p sub 1 of coefficients is simply 2, 0. Our second polynomial, p sub 2 of t, is defined as 2t. So vector p sub 2 of coefficients, we have no constant term, so a naught is 0, and a sub 1 is 2. And last but not least, we have p sub 3 of t, which is given to us as 8 minus 2t. And so therefore, the polynomial of coefficients, vector p sub 3, is defined as 8 minus 2. And so our indexed set of vectors is defined by the set containing these three vectors here. So we have p sub 1, p sub 2, and vector p sub 3. So I have 2, 0, 0, 2, and 8 minus 2. So now that we've determined our indexed set of vectors here, we're ready to go ahead and use our knowledge of how to determine if a set is linearly independent. So remember, we have that foolproof method of putting these three vectors into an augmented matrix with the 0 vector to determine if a free variable exists. So that's that's the foolproof method, but we could use shortcuts. Right, so you can always fall back on this method if you're not sure, or if you want to double check your answer. We can always put everything into an augmented matrix and double check that way. However, I want to look at a little shortcut here. So hopefully you're looking at this set of vectors and you're thinking, I have 1, 2, 3 vectors, but only 2 components per vector. So let's recall that if the number of vectors is greater than the number of entries per vector, then the set of vectors is automatically linearly dependent because a free variable will have to exist. And so this is the shortcut we're using here. We see that since there exist 3 vectors, which is greater than the 2 entries per vector, we can see that we automatically have a redundant vector. So the set of vectors is linearly dependent, or not linearly independent. And this is our beautiful final answer here. Now let's go ahead and take this one step further. While we've determined that this set is certainly not linearly independent, could we now use our knowledge of linear independence and linear dependence to find a dependence relation amongst these vectors? And by golly, yes we can. So let's take a look. So we've already determined that this index set of vectors defined by our polynomials here, or by the coefficients of our polynomials, is not linearly independent. So what we want to do is determine the dependence relation amongst these vectors, and then we'll be able to create a linearly independent set by removing the redundant vector. So let's take a peek. So again, we want to determine the dependence relation. So in other words, what vector is redundant of this set? So it could be more than one vector. Here it's just going to be one, but what vector is redundant? Which one depends on the other two vectors? So we are looking back here at our index set of vectors, and this third one, p sub 3, looks a little bit dubious. So let's take a peek here. What we want to do is let's pull out this vector p sub 3, which is 8, negative 2, and we want to try to rewrite it in terms of p sub 1 and p sub 2. So to get us started, I'm just going to break this down to a linear combination of the elementary vectors. So I have 8 times elementary vector e sub 1 plus a negative 2 multiplied by the elementary vector 0, 1. And looking at these coefficients, again, what I'm trying to do is rewrite this in terms of p sub 1 and p sub 2. So what about if we pull a 2 in on each? So with this first term, I'm going to leave 4 out in the front, and I distribute a 2 back through. And same thing with the second one. I'm going to leave a negative 1 out in front and distribute a 2 back through this elementary vector, so I have 0, 2. And lo and behold, we've done it. Now we have 4 multiplied by that elementary vector p sub 1 plus negative 1 multiplied by the elementary vector p sub 2. So we have rewritten p sub 3 in terms of the other two vectors. So p sub 3 is the redundant vector here. And so we can conclude that therefore the index set of vectors, if we remove this redundant vector, if we remove p sub 3, the remaining vectors is a linearly independent set. So by identifying your dependence relation, and then removing it, we end up with a linearly independent set.